started. Hey everyone, it is me, Mr. Kramer, and today for my stream I'm going to be going over the gas law practice problems. So if you watched my previous stream on May 13th, you will see me go over the definitions for kinetic molecular theory. I'll go over the practice assignment for the KMT. In fact, I'll go through all of the answers so you can see my reasoning for all of these. And I talk a little bit about the relationship between pressure, volume, temperature, and moles. And then in addition to that, I talk a decent bit about the relationship between a direct and an indirect relationship between two variables. Just as a review, a direct relationship, two things change together. In an indirect relationship, if one of them is going up, the other one has to be going down, and vice versa. So today, we're going to step beyond just the intuition or the general idea of this relationship and move on to some examples where we're really calculating, well, given some change in, say, temperature, what change should I expect up or down, and specifically what number will I see at the end for the volume or for the pressure or whatever variables that we're solving for. So this is really getting into the nitty-gritty of how how these formulas can be used to help solve problems. So I'm going to go ahead here and click the basic gas law notes and examples. So here, Mr. Ellingson went through the effort to give examples for each of these different types of problems. So he's an example for, he just kind of goes over all of them. He goes over a P and a V example, a V and a T example, and a P and a T example. And so basically in each of these cases, you have some change in one variable affecting the change in another variable. And that's really the beauty of science in general, is we've kind of distilled down all these crazy phenomena that are going on to some simple relationships between some variables that we can actually measure, which is also very useful. So my thought for today was that I would go through basically an example of each of these myself, but instead of doing it on a computer, I would do it on a piece of paper, like you might do on your own. And I think sometimes just seeing someone write it out with the hand can help with understanding. And then after I go through some examples of each, I will go ahead and do the practice quiz as we did with the KMT problems. I feel like going through, if someone's going to be watching along with me, I should take the time, and I'm going to take the time to do some problems. I feel like I should do the problems on the quiz just to help, incentivize you to watch. That way you can kind of see all of the answers and then also check your own work. So let's go back, though, to just the three different relationships we're going to focus on. And I'm going to switch over to my document camera, and then we're going to make this all happen. So here we are. Okay, sort of adjust my stance here. So I'm ready to go. Okay, so there's three possible relationships. And so for each one, there's an equation. So we're going to need three separate equations. So if P and V are related, it's written like this. And what this is saying is that the pressure at the beginning, so this is a little subscript to 1, so the pressure at the beginning and times the volume at the beginning. So there's no multiplication sign here, but anytime you have two variables next to each other, that's implied that they're multiplying. Now, I got to get this out of the way. We're not doing this is not a chemical equation. This is not the element phosphorus times the element vanadium or something like that. But rather is a mathematical equation. I got to make sure that it's visible. Just wanted to check on the live stream. It is. You can see this pretty well. I just need to make sure I continue to write big. Okay. So this is called Boyle's law, though I won't, you're not required to know that. Boyle's law. And basically, this says that if I ever have a pressure and a volume at the beginning, whatever they are at the beginning, that product, those numbers multiplied together, is actually a constant. So if one of these numbers changes or isn't a constant, the other one has to change correspondingly so that it remains the same total. So let me show you what that looks like. So let's say that I had a balloon. Here's my balloon. And inside this balloon, it's got a volume of 3 liters. And it has a pressure, I've blown it up, so it's got a pressure of, we'll say 1.5 times the atmosphere, ATM. So 1.5 times atmosphere, that means it's, if you imagine the pressure in the air around us, it's that same, it's half of that pressure added to it. So it's halfway between twice the pressure. And the volume of 3 liters, that's just the size that I picked for this balloon. So this is the state at the beginning. Now, let's say your kid brother comes along and starts messing with the balloon and starts trying to squeeze the balloon, because, you know, balloons are squishy, so maybe he wants to squeeze it. So this is state 1. When I squeeze the balloon, I need a better pen. This pen's trying to die on me. Let me get a better pen. This one's purple. This one's black. Got a few. We'll find. Hopefully, one of these is good. Not great. Really not great. Pretty good, but purple. I wonder how the purple shows up. Let me wait for it to show up on the camera. Oh, pretty decently. Okay, so we're going to use the purple one. Okay, so 1.5 ATMs. So I squeeze it, and then so at the end, we're shrinking the volume down. So V2, this means at the end, instead of 3 liters, it's gone down to 2 liters. So they shrunk the balloon from being this big to only being, it's being squished, so it's a little bit smaller. Same balloon, just a little bit smaller. So there's the same number of moles of gas in there. We're not going to allow the temperature to change. We're going to pretend like this is a, the temperature is insulated somehow. And what we want to know is, what is that pressure at the end? Now that I've decreased the volume, I want to know what the pressure is. Now, if you remember back to our relationship earlier, we found that pressure and volume are inversely related. So if you go back to our, and I'm going to have to do, bam, we're here. Here we are, continuing. Oh no, going backwards. Previous. Here we are. If we go back to this table, you might remember in Boyle's law, the volume and pressure are inversely proportional. So we know that when I decrease the pressure, that the volume is going to increase. But what the math is going to allow us to find out is by exactly how much. It's the exact same reasoning. In general, those particles are getting squished together, so there's more collisions inside the balloons that's going to cause an increase in pressure. Okay, so we're going to use this equation up here. And let me switch back to the thing. Okay, we're going to use this equation up here using these numbers to sort out what the answer is. So I'm going to set up my equation here, P1. V1. So it's the pressure at the beginning times the volume at the beginning, and that's a product that I could find out. And then here at the end, I have pressure 2 times volume 2. So let's start by putting pressure 1 and volume 1 in there. So pressure 1 was 1.5 ATMs, and this was 3 liters. So when I multiply those two things together, on this side, still on the left side of the equation, this is 4.5. So this is 4.5. Whatever's on this side of the equation has to also be 4.5. But we know that one of these things has changed. So the pressure, volume 2, pressure 2 is what we're solving for. Volume 2 has changed. It used to be 3, but now it's 2. 2 liters. So there's a difference here. So even though there's a difference between the volume variable, the whole left side still has to equal the whole right side. So the pressure has to change to basically account for this change in the volume. So we're left with 4.5 equals P2 times basically the number 2. And then at this point, I need to get the pressure 2 by itself. So I'm going to divide both sides by 2. When I do that, I have pressure 2 on this side, so these cancel out. On this side, I have 4.5 divided by 2, which is 2.25. Now, you can use a calculator to solve this if you want to. So this is going to be my pressure in ATMs. So when I squeeze the balloon from 3 liters down to 2 liters, the pressure has to go up. So it goes up from 1.5 all the way up to 2.25 ATMs if I squeezed it from 3 to 2 liters. So that's one way of executing Boyle's law to find the difference in pressure. So we're going to do 2 more examples, not with Boyle's law, but with the other laws. So this is Boyle's law, pressure and volume. Now, I'm not going to do an example, but you can do, the problem is exactly the same if instead the pressure is the one that I know the change in and I'm trying to find the volume. It would look very similar. For example, let's say that I knew somehow that the pressure at the end was 2.25, but I didn't know what volume it was. So I'd go through the same, maybe I will show an example. P2, V2. So let's see if this works. So this is still the same, 1.5 times 3 liters. So the left side hasn't changed. This is still 4.5. But now on this side, I know that P2 is 2.25. But I don't know what the volume is, so I'm trying to find the volume. This is like this is like the bizarro world for this problem, where instead of knowing the volume, I know the pressure. Okay, so I still have a variable here that I'm looking for. So I need to divide both sides by 2.25. I should have written this on this line. It's 2.25 times V2. So I'm going to divide both sides by 2.25. These are going to cancel out. So on this side, I'll have V2. And then on this side, I have this fraction, 4.5 divided by 2.25. Now, this one's a little bit harder to maybe do in your head or whatever. So I can switch over just so you know I'm not lying to you. So I can type in 4.5 divided by 2.25 and see what comes up. Oh, indeed, it pops up with the number 2. That would imply that this at the end, if I go, oops, let me go back to this at the end says that the final volume, 4.5 divided by 2.25, should be 2 liters, which is the final volume. So no matter which way I'm doing the problem, I use very similar steps. I plug in what I know, and then in this case, I'm going to be dividing by whichever number is not the variable to keep the variable by itself at the end so that we can solve the problem. Okay. Great. So this is Boyle's law, which is the relationship between pressure and volume. And the way you know to use this law, well, in this case, is very obvious. But anytime you have given the initial pressure and volume of a system, you're probably going to be using this. So if I say it's got this many liters and this many atmospheres, or sometimes, this many gallons and this many other units for pressure can be kilopascals, which is like, you saw this in my previous video, but it's just another unit for pressure. You can also sometimes see PSI. This is like what you use in your bike pump, so that's pounds per square inch. These are all just different units for pressure, which is a little bit confusing, but it should be clear in the problems that you're going to be doing for this class. Okay, so moving on. So that's Boyle's law. Maybe I'll put a timestamp in this video with all the different laws. Pressure times volume. All right, next, if I want to, let's get temperature involved. So we're still talking about a balloon, but I still have a balloon, but I'm going to heat up the air inside the balloon. That's my plan. This is very dangerous because if you heat up a balloon, it might pop, but we'll see what happens. So the relationship between temperature and volume is called Charles' law. Charles's law, depending on how you pronounce that. So Charles's law is a little bit different. Remember, if we go back to our teaching table, the volume and temperature are related directly. So if one of them increases, then the other one should also increase. So for us, that looks mathematically a little bit different from what we saw before. So here we have, now I got to make sure I do it the way that I want to be consistent. There's actually two ways to write this. So I want to write it the right way. Do we put the temperature on the bottom probably? Since that's consistent with the, yeah, we put temperature on the bottom. Okay, great. So here we have volume at the beginning divided by the temperature at the beginning. So this is a fraction now. Previously we had two numbers multiplied together, but the fraction here is also going to be a constant. So at the end, the volume at the end divided by the temperature at the end is going to equal the same thing. Now, if one of those changes, the other one also has to change so that the fraction remains the same. So how are we going to do that? Let me just turn this a little bit because I think I keep turning my paper. It's all right a bit. Okay. So again, we have a balloon. I'm not very good at drawing balloons. Here it is at the beginning. Let's say that it's the same volume, so it's a 3-liter balloon. And the temperature, now the temperature has to be given in Kelvin or Rankine. So we're going to say that V1 equals 3 liters and that T1 equals, we'll say 300 Kelvin. That's going to make our numbers very nice and easy to use. So then what we do to get to state 2 is we have the same balloon, but we've put like a little flame under it. So let me draw a little Bunsen burner. So you have a little Bunsen burner with it's a little base and it's got its thing, and then there's some flames coming out of it. Now, the problem here, of course, is that this would pop the balloon, but we're going to pretend that it doesn't. So here we got the balloon. Its temperature is going to go up. So let's say that the temperature at the end equals 500 Kelvin. So we increased it 200 degrees. That's crazy. That's a really big increase in temperature. So this balloon is going to, if our understanding of Charles' law is correct, temperature and volume are directly related, which means that if one goes up, the other one has to also go up. So in this case, that means that since the temperature is going up, the volume should go up as well, but the question is how much? And so that's where the equation up here is going to help us out. So let's set up this equation, plug in what we know, and see what's going on. So we have V1 over T1 equals V2 over T2. In this case, I know V1 and T1, so I'm going to plug those in. V1 is 3 and T1 is 300. Okay, L. And then over here, I don't know V2, that's a variable. And then T2, I also know it's 500. So now, this could get tricky for some of you. I'm going to encourage you to cross multiply. For this problem, it's a little bit easier than that, but I don't want to confuse the math. So anytime you have fractions like this and a variable on one side, you always want to cross multiply. So you're going to do 3 times 500 and 300 times V, so cross multiply. So I'm going to do this on this side, so 3 times 500, and that's going to equal 300 times V2. So 3 times 500 is 1,500, and this is, of course, 300 V2. And then at the end, to get to the last step, you just got to divide. So 300, that goes away. Divide by 300, that goes away. That doesn't go away, but this divides into, I believe it's just 5. 5 liters equals V2. So here at the end of it, we come up with a final volume of 5 liters, which is a nice round answer. And we see that our intuition checks out. I increased the temperature from 300 to 500 degrees using my little Bunsen burner flame. And the volume, this got bigger. So you can imagine this kind of blowing up a little bit. It went from 3 liters to 5 liters. So that's great. Now I'm going to quickly show it going the other way, and then I'll do the last example. So what if instead of being able to measure the temperature, I was able to measure the volume of the balloon? So it's the exact same problem. V1 T1 equals V2 over T2. I knew that I started with 3 liters at 300K. By the way, 300K is like is like a very warm room temperature. So that's like normal temperature. 300 is not a big number for Kelvin. And then at the end, instead of knowing that it went up to 500 degrees Kelvin, let's say I was able to measure that the balloon was 5 liters big, based on, some measure. Either I put it underwater, volume displacement, or whatever. I'm just estimating that it's, almost doubled in size. So I know that it went up to 5 liters, but then I don't know what the final temperature was. So I can actually use the change in volume of this balloon as a way of, it's like a thermometer to measure the final temperature. Isn't that kind of cool? So, and we'll check to see if we get the same answer that we got before. So here I am, I've got this over this equals this over this. So I need to cross multiply again. So cross multiply, so these two numbers together. So 3 times T2 equals 300 times 5, which is 1,500 again. I believe that's right. And then now I need to do, I have T2 still, it's not by itself, so I'm going to do some dividing. So divide by 3, divide both sides by 3. That cancels out. So you have T2 equals 1,500 divided by 3, which is 500. Okay. So in fact, we got the same answer that we started with, 500 Kelvin, 500 Kelvin. And you can see that actually, like I said, we can use the change in volume of this balloon like a thermometer to measure how much the gas is heated up. So that's, this is all assuming, of course, that we're at a constant pressure, which is not a perfect assumption, but imagine that somehow this balloon was expanding without the need to basically strain its, its rubber anymore. So there's a bit of a. This wouldn't exactly work in real life, but you could develop a system that would work the same way if you would like to, using pistons, for example. Okay, so that's Charles' law, and we got one more law to do, which is the Gay-Lussac law. So I'm going to go back to my, well, let's see if I can spell Gay-Lussac first. So Gay, and then another person, Lussac. And this relationship goes between pressure and temperature. So pressure and temperature. So let's go back to our table, and then previous. Look at this. Okay, so the Gay-Lussac law, pressure and temperature, these are also related directly. So they're also directly proportional. So this is going to look just like the problem we did with Charles' law. However, instead of volume, we're going to be looking at pressure. So this time, imagine that I don't have a balloon, because balloons change their volume when you increase the pressure, the temperature, whatever. So let's pick something that's volume doesn't change. Often this is called a rigid container. So I'm going to use something that is like a balloon, but is instead, but what doesn't change its volume very much. And so for that, I'm going to pretend that we're talking about a car tire. So imagine you got a car tire. Okay, so technical difficulties. I forgot to switch over to the right screen. So I already did some work here, but I'm going to go through it step by step. So I have a tire that I'm driving around. I believe I got this far. It has 3 atm of an initial pressure, so that's like 3 times the atmospheric pressure inside your tire. And it's 300 K, which is the same sort of like room temperature or whatever. Maybe it's 300 degrees outside. So I'm going to use the Gay-Lussac law, which says that I have, just like the Charles law, I have pressure 1 and temperature 1 in a fraction. And so this fraction is a constant. And on the other side, I have P2 over T2. So this ratio stays the same, but if one of them changes, the other one has to change to compensate. So let's go through the math. So I have P1, T1. So that's going to be the initial pressure here, so 3 atms. And then the final temperature, the initial temperature, 300 Kelvin. So my starting conditions over here in a fraction. And what I said was that after driving around, the temperature increased to 350 Kelvin. So what I'm saying is, I drive around. If you've ever touched a car after it's been driven or touched the tires, they're quite a bit hotter than the air outside. So that change in temperature is actually going to cause a change in pressure in the tires. So So my final temperature is T2. The question I'm trying to solve is, hey, what would be that pressure at the end of the day inside my tires after I've been driving around? So I have this in 3 over 300, and this is P over 350. So I'm going to have to cross multiply. So 3 times 350 right there, and then 300 times P right there. So this is just a classic cross multiplying situation. And then next, I'm going to need to multiply these two together. That gives me 1,050. So 3 times 350 equals 1,050. And then on this side, I don't have to do anything except divide by 300. So then after I found this, I'm going to divide both sides by 300. And it's going to give me my answer. That's going to cancel out. So on this side, I have P2 right there. And then on this side, I have 1,050 divided by 300, which I did on a calculator, gives me 3.5 ATM. So basically what this is saying is, if I increase the temperature from 300 degrees Kelvin to 350 degrees Kelvin, then my pressure is going to go up to 3.5 ATM. So it's going to increase from 3 to 3.5. That's another basically half times the whole atmospheric pressure jammed into your tire. Or if this was in PSI, if this started around 30 PSI, this would go up to something like 37-ish PSI, I'm pretty sure. So if you were using a normal pressure gauge, that's what you would see. And then what I was going to do is this. So assuming instead you didn't have a thermometer to stick inside your tire to measure the air temperature, but you had a pressure gauge and you measured this 3.5 ATMs after your drive, and you wanted to say, I can see that my pressure is now increased, but I wonder what has happened to my temperature. So you can use the same equation, but solve for temperature instead of for pressure. So my initial conditions are the same. I start with 3 ATMs over 300 Kelvin. So I'm still using my initial pressure and my initial temperature, so P1 and T1. And that's going to equal P2 over T2. Now, in this case, I know P2. It's 3.5 ATMs. I measured that with my pressure gauge that I stuck onto my car. And then what I'm wondering is, I wonder how hot that got. And we're going to double check that we get the same answer. So again, I need to cross multiply. So 3 times T2 on this side, so 3 times T2. And on this side, 300 times 3.5. So 300 times 3.5 is going to be, it's going to be the same, 1,050. It's got to be. All right, so 1,050. So then I have 3 times T2 equals 1,050. So I need to divide both sides by 3. Easy peasy. So this is going to cancel out. And then 1,050 divided by 3. So T2 will be on this side. This fraction divided by each other is 350. Okay. So no matter which way I do it, the Gay-Lussac law will give me the relationship between pressure and temperature. If the pressure is changing, then the temperature will change with it. They'll both increase, and vice versa. If one is decreasing, the other one will decrease to keep these fractions the same. But the way you do it is just by cross-multiplying anytime you have the starting condition and you're trying to find one of the ending conditions. So hopefully that was helpful for you. I said I was going to do the practice problems, but I feel like I did enough practice problems. I don't want to waste any more time. So enjoy the weekend, and hopefully this cleared things up for you a little bit. Maybe just to review, to put all the laws together. Let's see, do I have them all on separate sheets of paper? I thought I did. I don't. Oh, that's too bad. So we had the Gay-Lussac law, which was pressure P1 over T1 equals P2 over T2. We have Boyle's law, which is P1 V1 equals P2 times V2. So this one's nice because you don't have to cross multiply. And then the other one where you do have to cross multiply is the Charles law, which is V1 over T1 equals V2 over T2. And so we'll always give you these on tests and quizzes. And these same relationships are going to kind of get combined later and pop up together when we're using the ideal gas law. And so look forward to that for next week. But until then, take care.